Hey everyone, and welcome back to the channel. Today, we continue our journey on Kaggle competition, equity in post-HCT survival predictions. The goal is to predict patient survival after a hematopoietic cell transplant, HCT, a really important and complex medical challenge. I've been exploring a fantastic notebook called GPU LightGBM Baseline by the Kaggle Grandmaster Chris Deotte, and I've learned a ton from it. I want to walk you through it, not as an expert, but as a fellow learner, and share the key ideas and techniques. All right, let's jump in. The notebook's introduction lays out the groundwork. It highlights some really cool things, including transforming the target variable using something called Kaplan-Meier fitter, and training several models like GPU LightGBM, XGBoost, and CatBoost with survival-specific loss functions. It even shows how to ensemble them, which is like combining the strengths of multiple models to get an even better prediction. The author points out that there are two main ways to tackle this competition. You can either train a model that directly understands survival analysis using a survival loss, like the Cox Proportional Hazards model, or you can transform the two target variables, F's, event-free survival, and F's time to event or censoring, into a single risk score and use a regular regression model. This notebook explores both approaches, which is super insightful. First up, we need to install a library called Lifelines. Because Kaggle submissions require internet to be turned off, the author cleverly provides the necessary files, wheel files, specifically from another notebook. This is a practical tip for Kaggle competitions. We're just installing some tools we'll need later. Now we're loading the data. We've got a train data and a test data. Let's see. The test set has 58 columns and the training set has 60. And we get a peek at the first few rows of the training data. We see a bunch of features. Things like dry score, psych disturb, cyto score, HLA match, and so on. These are all factors that could potentially influence a patient's survival after the transplant. This is where it gets really interesting. We have two target variables, F's and F's time. F's tells us if an event occurred like a relapse or, sadly, death. F's time tells us when that event happened, or if no event occurred, F's is 0, how long the patient was observed without the event. This histogram is key to understanding the challenge. The blue bars show the distribution of F's time when an event did happen, F's equals 1. The orange bars show F's time when an event didn't happen during the observation period, F's equals 0. Notice how the blue bars are clustered towards shorter times. That means a lot of events happen relatively soon after the transplant. The orange bars represent what's called censored data. We don't know if or when the event will happen, just that it hadn't happened yet. This is a classic survival analysis problem, and it means we can't just use standard regression techniques. Here's where the Kaplan-Meier fitter from the Lifelines library comes in. It's a way to estimate the survival function, the probability of surviving past a certain time. The notebook uses it to transform F's and F's time into a single target variable, why this Y value represents an estimate of the survival probability at the observed time. Look at this histogram of the transformed target. Why again, we see the blue bars F's equals 1 and orange bars F's equals 0. The Y values for patients who had an event blue are more spread out, while the Y values for patients who didn't have an event orange are clustered higher, closer to 1. This transformation makes it possible to use regression models, even with this censored data. Next, we prepare the features. The notebook identifies 57 features, and a good chunk of them, 35, are categorical, meaning they represent categories, not numbers like yes, no, or different disease types. The notebook fills in any missing values in these categorical features with the string nan. Then, it uses a technique called label encoding to convert these categories into numerical representations. This is important because many machine learning models work best with numerical input. It also reduces the precision of numerical features to save memory, which is a good practice, especially with larger datasets. Now for the modeling. The notebook starts with XGBoost, a powerful gradient boosting algorithm. It trains the model using 10-fold cross-validation. This means the data is split into 10 parts, the model is trained on 9 parts and validated on the remaining part, and this is repeated 10 times with different splits. This gives us a more robust estimate of how well the model generalizes. We see some key parameters being set: max depth, call sample by tree, subsample, N estimators, learning rate, and importantly, enable categorical equals true. This last one tells XGBoost to handle the categorical features we encoded earlier. The model trains, and we see the root mean squared error, RMSE, on the validation set decreasing with each iteration. This is good. It means the model is learning. Here, the notebook uses a custom metric, defined in a separate file, to evaluate the model's performance. The cross-validation CV score for XGBoost with the Kaplan-Meier transform target is about 0.674. This metric, called a concordance index, measures how well the model ranks patients by their risk. A higher score is better. This is a fantastic plot. It shows us which features are most important for the XGBoost model. Conditioning intensity, dry score, and comorbidity score are at the top. This makes intuitive sense. The intensity of the pre-transplant treatment, the donor's risk, and the patient's overall health are all likely to be major factors in survival. It's great to see the model picking up on these clinically relevant variables. The notebook then repeats a similar process with CatBoost, another powerful gradient boosting algorithm. The setup is very similar, with 10-fold cross-validation and similar parameters. Notice that CatBoost also has a parameter to handle categorical features directly, cat features equals cats. The training output shows the loss decreasing over iterations. The CatBoost model achieves a very similar CV score of around 0.674. The CatBoost feature importance plot is also very interesting. Dry score and conditioning intensity are again very important, along with comorbidity score, year HCT, and donor age. The consistency between the XGBoost and CatBoost feature importances gives us more confidence in these findings. Next up is LightGBM, another popular gradient boosting library. It's known for being very fast, especially on GPUs. The training process is the same as before. The CV score for LightGBM is slightly lower, around 0.672. The LightGBM feature importance plot shows some differences. Donor age and age at HCT are the most important, followed by dry score and prim disease HCT. This highlights that different models can pick up on slightly different patterns in the data. Now, the notebook switches gears and uses the second approach mentioned at the beginning, directly modeling survival using a Cox Proportional Hazards loss function within XGBoost. This is a clever trick. To use the Cox loss, we need to modify the F's time variable. If F's is 0, no event, the corresponding F's time is multiplied by -1. This tells the Cox model that these are censored observations. We train XGBoost again, but this time with objective equals survival, Cox, and eval metric equals CoxN logLic. The CV score is around 0.672. The feature importance plot for the Cox model is slightly different again, with conditioning intensity and graph type being the most important. Finally, the notebook does the same thing with CatBoost, using the loss function equals Cox. The CV score for CatBoost with Cox loss is around 0.671. The CatBoost Cox feature importance plot is broadly similar to the XGBoost Cox plot, with conditioning intensity, comorbidity score, and year HCT being high up. This is the grand finale. The notebook ensembles all 5 models, the 3 Kaplan-Meier models, XGBoost, CatBoost, LightGBM, and the 2 Cox models, XGBoost, CatBoost. It does this by using CIBMTR, stats, rank data. This converts each model's predictions into ranks, and then it simply adds the ranks together. And the result? The ensemble achieves a CV score of 0.681. This is higher than any of the individual models. This demonstrates the power of ensembling. Combining different models can often lead to better performance. Finally, the notebook creates a submission file, submission data, using the ensemble predictions. This file is what you would submit to the Kaggle competition. Wow, that was a lot. We covered Kaplan-Meier survival analysis, gradient boosting with XGBoost, CatBoost, and LightGBM, Cox Proportional Hazards, feature importance, and ensembling. This notebook is a fantastic resource for anyone interested in survival analysis or Kaggle competitions. I highly recommend checking it out. I'll leave a link in the description. Remember, I'm still learning too, so if you have any questions or insights, please share them in the comments below. And as always, if you found this video helpful, please like and subscribe for more data science adventures. Thanks for watching.